Today I'll be talking about the work that our group has been doing towards demonstrating large-scale simulations of systems relevant to quantum chemistry and material science on quantum computers using a combination of the recently proposed sample-based diagonalization and quantum bootstrap embedding. So just to be explicit on what we're doing, we're interested in solving for the ground state of the electronic structure Hamiltonian for quantum chemistry systems. And so in order to do this, you of course need a quantum eigensolver that you can run on your quantum computer. I'll just very briefly go over them. The first of them that was proposed several decades ago at this point is quantum phase estimation, which has a provable exponential speedup over the exact classical case, at least given certain reasonable assumptions. The issue with this, of course, is that the circuit depths involved are far too deep to be practically implemented on near-term hardware. And from this came the motivation for the proposal of VQE, where you suppose you have a very shallow depth ansatz that's parameterized, and you just measure the expectation value of your Hamiltonian and variational optimize these parameters using something like gradient descent. The drawback to this is that when you consider scaling this up to systems large enough to where quantum advantage becomes plausible, so on the order of hundreds or thousands of spin orbitals, the number of terms in the Hamiltonian whose expectation values you need to measure grows quite large, and this can cause the runtime for even one energy estimation for VQE to become prohibitively long, even before you can take into consideration other hurdles that you could encounter, such as barren plateaus. And this motivated the proposal of of sample-based diagonalization. I'll just very briefly go over what that is. So, if phase estimation and VQE are quantum eigensolvers, where you find the eigenstate on your quantum computer, then sample-based diagonalization and other quantum select configuration interaction methods basically just use the quantum computer to find the optimal subspace in which you should perform a truncated diagonalization problem. And so the idea is that you sample from your ansatz circuit, and you collect samples to get a probability distribution over the set of bit strings that you have measured. You can subsample from this probability distribution and group these into batches, and you can perform select CI classical diagonalization steps in the subspaces spanned by all the states in these batches. And so in doing so, you avoid ever having to take an expectation value of a Hamiltonian with a large number of terms in it on your quantum computer. The drawback, of course, is that because now your diagonalization step is done classically, you have to assume that your quantum state can be well approximated by a CI expansion of polynomial size. And now you have to find a suitable ansatz that can capture what this optimal subspace is using only classical inputs, which is also non-trivial. And so we're looking to combine this method with quantum bootstrap embedding, where on a high level, you can think of the guiding principle behind quantum bootstrap embedding to be that we assume that the entanglement of your large system is at least reasonably local enough that you can consider breaking up this large system into overlapping fragments and then try reclaiming some of this correlation by applying matching conditions on the overlapping regions, such as matching the 1 or the 1 and 2 RDMs on these overlapping sites between neighboring fragments. And so essentially what we're doing is just performing a constrained optimization problem where we want to minimize the expectation value of our collection of fragment Hamiltonians subject to certain matching conditions, where here we have our Lagrange multipliers lambda AB dot product with a vectorized representation of the difference between the RDMs of the overlapping sites of our neighboring fragments. And the last term is just applying the constraint where we want to constrain what the number of particles in our system is. And so the questions we would like to answer are, is can QBE used in combination with something that is very NISQ-friendly like SQD? Can it be used to scale up and expand what size of the systems we can simulate on current hardware? And furthermore, we will also like to ask the question of, can we take the output from QBE, which returns a set of fragment states, and can we reconstruct what an estimate for what the global wave function is of the entire system that we're trying to study? So here is a brief overview of our experimental setup. Right now, we have a hydrogen chain of length 8 in a minimal basis, and we're breaking up into 6 fragments of 3 hydrogen atoms each. And for now, we are classically simulating this on Qiskit-fake backends, but we're looking to run this on actual hardware in the near future. We're doing 10 to 3 shots per fragment with 10 SQD shots per SQD solver per fragment. We're doing 20 optimization loops of this Bootstrap Embedding method. And we're using this local unitary couple cluster Jasper ansatz, which you can just think of this as a couple cluster style ansatz with classically pre-computed CCSD parameters, whose coupling terms match the qubit connectivity of the device that you're trying to run this on. This is an important step for trying to ensure that you don't have a large circuit depth overhead associated with compilation. So in the blue and red dots here, on this qubit connectivity graph, these are the qubits which encode our alpha and beta orbitals respectively, and the purple lines indicate which alpha beta coupling terms are explicitly included in our ansatz. And so here's some preliminary results that we've achieved on these Qiskit-fake backends. So here we are plotting the mean energy error achieved by this method, averaged over 10 runs of this method, against the exact FCI value of the entire system. And we're plotting this as a function of the number of samples in each batch for the SQD solver for each fragment. And so you can think of this very roughly as a measure of how much of the full CI space you're saturating every time you want to find the ground state of each fragment. So on the low end, where we achieve an accuracy about 15 millihartree, this is using maybe 50 to 75% of the full CI space. And towards the low end, or towards the high end, we're using about 30 samples per batch. This is using about maybe 90 to 100% of the full CI space. So to me, this indicates a need to I think, further scrutinize and learn how to improve these quantum select configuration interaction methods such that they are truly finding a compact subspace and that you're not just recovering the full CI complexity. And furthermore, we would also like to take the output from QBE and return an estimate for an approximation for the reconstructed wave function of the entire system. So QBE only returns you a set of fragment states which emit a CI expansion like so. But what if you wanted to compute a property of your system that you couldn't do using the energy alone? So maybe you wanted to compute the electric dipole moment or something like that. So we can take inspiration from SQD to develop a heuristic for what might be a good support for this wave function. And if we can find a good support from it, then we can take the states in this support as an input to SQD and have it return an estimate for the wave function. So the principle behind QB is that once you minimize your Lagrangian, you're supposed to get a collection of fragment states which match on their overlapping segments. So maybe a good heuristic for the support is to say that you want to find all bit strings such that on their overlapping regions, they have the same bits. And so you can loop over all fragments, you can loop over all bit strings for all these fragments and check this matching condition. And if they do match, then you can conjoin them and add them to your CI space that you're wanting to find and pass them to SQD. And so here are some preliminary results that we've achieved. So we are plotting the fidelity of this reconstructed wave function against the full CI state of your entire system as a function of the ratio of the dimension to of this state that you constructed with the full CI space. So you can think of this as how much of the full CI space do you need to saturate in order to get a certain fidelity. And we see that towards the low end, where we use maybe 20% of this full CI space, we get maybe 80% fidelity. At around half, we get maybe 95, and around 70%, we get around 98 to 99 fidelity. And so in conclusion, what we've demonstrated is that SQD can indeed serve as a suitable eigensolver subroutine for this quantum bootstrap embedding method. However, there is a need to take a closer look at these quantum select configuration interaction methods to make sure that they are indeed finding a compact subspace and that you are not just recovering the full CI complexity. And we've also demonstrated a proof of principle that you can take the outputs from QBE and use it to reconstruct an approximation for what the global wave function is. And the next steps are that we would like to scale this up to larger systems, so ideally at least 30 qubits per fragment, and run them on actual quantum hardware. And because it seems that the Achilles heel of these quantum select configuration interaction methods, or you will, are the state that you use to sample from to find what this optimal subspace is. We want to further investigate this aspect of it so that we can make sure that our methods are as efficient as possible. And we would also like to investigate how well the state reconstruction scales well to larger systems, or whether it simply breaks down. And in the event that it breaks down, we would like to investigate whether there are more sophisticated, more efficient ways to do this. Thank you.